Hello and welcome to a new video series. We're going to be looking at adding i2c modules to our projects on our Agon and communicating using z80 assembly language. This is a typical module we might be using. This example provides an extra 8 digital input-output ports. The i2c communications bus requires 4 wires. Voltage at 3.3 volts, ground, SDA and SCL. You can find these connections on the back of your Agon i2c on the left hand side. The positive voltage, the ground, the SCL and the SDA connections. If you're using Agon i2c, you can also use the UEXT connector. You can see here which pins are used for each of the wires. If you're using a console 8, then opening up the top reveals the connections, in the similar place to the Agon i2c on the left hand side. We're not restricted to just one module. Every module has its own address, and that will be of a 7-bit value, from 0 to 127, although we usually use the notation from 0 to 7F in hexadecimal. Out of the factory, most units come with a fixed address already assigned. However, some of these can be changed with jumpers or solder pads, or dip switches if you're lucky. In our example here, there are 3 jumpers. That gives us 8 different permutations of addresses that we could use. On any i2c bus, there must always be one master, and that's going to be our Agon. You can have many different slaves, that is our modules, as long as each one has a different address. Normally, the master will send out a command. It might then also send out some data, or read some data from the slave. Whether we're writing our code in BASIC, in C or Z80 assembler, the MOS operating system provides us with 4 commands to help us. Commands to open the i2c bus and to close it, as well as writing data and reading data. The i2c open command takes one parameter, and that we put into the C register. It will be 1, 2 or 3 depending on what frequency we want the communication to run at. Most will work on 3. At this point we haven't actually defined what slave we're going to be talking to, simply that we're opening up the i2c bus for communications. The i2c close command is really simple. It takes no parameters and simply closes the bus. The i2c write command is where it starts to get a little bit more complicated. We put the bus ID of the slave we want to communicate with in the C register, and in the B register we put the number of bytes we actually want to send to that slave. There's a maximum of 32 allowed. The bytes we're actually going to be sending are stored at a location which is pointed to by the HL register. So we'll normally set up a buffer for where we want to store that. The i2c read command is pretty similar to the write one. We put the bus ID of the slave we want to talk to into the register C, and the number of bytes we want to read will be put into B. This time HL will store a pointer to a buffer where we're actually going to save the data, which is read from the slave. There are lots of different i2c modules available to add to our projects on our Agon. We've already seen one example of an I/O port expander. There are modules to measure temperature, humidity, pressure, real-time clocks with battery backup, modules to convert analog to digital signals, and vice versa from digital to analog. We can also use game controllers, such as a Wii Nunchuck controller. There are LCD and LED displays, or you could build your own custom module, maybe with a Raspberry Pi Pico, using the Python i2c library. Through this series, we aim to look at how we might communicate with these i2c modules using ZHE assembly on our Agon.